Emma, and I'm going to teach you about the hot chocolate effect. Check this out.
I've just added some powdered hot chocolate to this mug of hot water. Pay close attention to the pitch of the taps as they will rise over time.
So, why does this happen? Let's take a look at the physics.
A cylindrical column of fluid will resonate at a natural frequency determined by three physical properties. H, the height of the fluid column, ρ, the mass density of the fluid, and kappa, the adiabatic bulk modulus of the fluid. That's a measure of how compressible the fluid is. The higher the bulk modulus, the harder it is to compress. Our mug of warm water can be modeled by two fluid columns stacked on top of each other. On top, we have a column of air, which will resonate at a frequency of about 1500 Hz. On the bottom, we have a column of water, which will resonate at a frequency of about 3000 Hz. You'll notice that I haven't chosen the fundamental frequency for either column. That's because these fundamental frequencies lie in the fringe of human hearing. That means that even though they'll have the biggest resonant effect, you won't hear them as well as you hear these harmonics, which fall right in the sweet spot of your hearing. When we add hot chocolate powder to our water, we introduce bubbles, which are highly compressible. Our top column of air will still resonate at the same frequency, since we haven't changed anything about it. But our bottom column, now made of hot chocolate, will have a different resonant frequency than the water did. That resonant frequency will be determined by its bulk modulus and by its mass density, since we haven't changed the height. The mass density of hot chocolate is essentially that of water, since the air bubbles take up a very small volume. But the bulk modulus is much smaller than that of water, because it's very easy to compress those air bubbles. That means that the resonant frequency of this bubbly hot chocolate will be much lower than the resonant frequency of the water. As the bubbles leave the hot chocolate, the bulk modulus of the hot chocolate will get closer and closer to that of water, until they're essentially equal, giving us the same resonant frequency we started with. To see this in action, let's head to the lab. I start with 250 milliliters of hot tap water and add 1 tablespoon of hot chocolate powder. I give it 20 stirs to keep that constant across my trials. To help us see what's going on, I've included the power spectrum of the audio at the right. Pay close attention to that peak in the middle. The left orange line shows its starting position, and the right orange line shows its final position. That's the resonant frequency of our hot chocolate. You might also notice a peak to the left of the first orange line that's not changing with time. That's the resonant frequency of the air column sitting on top of the hot chocolate. Here's a good way to visualize our results. We have frequency plotted versus time, with color indicating intensity. Each one of those vertical lines is a tap of the spoon. Here we see a line at 1500 Hz. That's resonance from the air column on top of the hot chocolate. See how it stays constant throughout the whole experiment? This curve is resonance from the hot chocolate. It starts at 1600 Hz, rises as the bubbles dissipate, and levels off at 3000 Hz, the frequency we calculated for just a column of water. Now to really put this theory to the test, I repeated the process for various volumes of hot chocolate powder and recorded the initial and final frequencies for each. Let's take a look at that data. The blue dots are the initial frequency, which gets lower as we increase the volume of hot chocolate powder. This is because the volume of hot chocolate powder is acting as a proxy for the volume of bubbles in the hot chocolate. As we add more powder, more bubbles form, making the hot chocolate more easily compressible and giving it a lower fundamental frequency. The orange dots are the final frequency, which doesn't change as we change the volume of hot chocolate powder. This is because by the time all the bubbles have dissipated, the hot chocolate has essentially the same properties regardless of how much hot chocolate powder we've put in, and thus will have the same resonant frequency. Pretty cool, huh? I hope you enjoyed learning about the hot chocolate effect. Next time you're having hot chocolate with a friend, tell them a little bit about the physics. It also works with powdered coffee creamer if you're more into that game. There's also a lot yet to be studied about this effect. I only looked at the initial and final frequencies for my experiment, but the curves along the way are really interesting to look at. All you need is some hot chocolate powder, a mug, and a microphone to get started. I'd encourage you to take a look.